This is electrostatic forces in a square, a worked example. The problem is a 2 microcoulomb charge is placed on one corner of a 10 by 10 square. A 3 microcoulomb charge is placed on a second corner. A -4 microcoulomb charge is placed on a third corner. A 5 microcoulomb charge is placed on the fourth corner. Then the question is threefold. 1. What is the net force on the first charge? 2. What is the net force on the second charge? And 3. What is the net force on the third charge? It helps to visualize it, and we're looking particularly at the forces on the first, second, and third charge. It is helpful to have a chart to keep track of all the information that we're going to be getting. In particular, we're looking at the forces exerted on charge Q1 by charges 2, 3, and 4. The forces exerted on charge Q2 by charges 1, 3, and 4. And the forces exerted on charge Q3. We can only handle pairs of forces one at a time. So we're going to look at the forces on 1 by 2, the force exerted on 1 by 3, the force exerted on 1 by 4, the force exerted on 2 by 1, the force exerted on 2 by 3, the force exerted on 2 by 4, the force exerted on 3 by 1, the force exerted on 3 by 2, and the force exerted on 3 by 4. After we get the chart made, the next thing to do is just some brute force calculations. So we're going to just use Coulomb's law to come up with the calculations. You can see that I'm writing the force on charge 1 by charge 4, and then I'm putting in Coulomb's law, the Coulomb's constant K, times charge 1, Q1, times charge 4, Q4, divided by the distance from 1 to 4 squared. I'm going to do that for all the charges. In terms of symmetry, even though there are 9 separate charges on our chart, we only have to worry about 6 of them, because the force between 1 and 2 is equal, although opposite, to the force between 2 and 1, and so on. So we have less computational work to do. After I've gotten the formulas written, I'm now going to go back in and plug in the correct numbers. The first force, that between charge Q1 and Q2, it's straightforward in doing the substitution. We have K, 8.99 times 10 to the 9th. We have Q1, 2 microcoulombs. Q2, 3 microcoulombs. And of course the distance between charge Q1 and Q2, 0.1 meters, 10 centimeters, and that distance of course is squared. The difficulty comes into play when we want to calculate the distance between charge Q1 and charge Q3, because it's not simply one side of the square. It's the distance from one corner to the other corner of the square. One side is 0.1 meters, and the other side is 0.1 meters, and it stands to reason the hypotenuse is equal to the square root of 0.1 squared plus 0.1 squared. I can now go on and fill in some of these other numbers. So the force between charge 1 and 3 is equal to 8.99 times 10 to the 9th times 2 microcoulombs times 4 microcoulombs divided by the square root of 0.1 squared plus 0.1 squared, that quantity squared. I'm dropping the negative sign for the negative charge on 4 microcoulombs. All I want to do at this point is get a magnitude. I'm going to analyze whether it's a positive force or a negative force after I do all of my mathematics. Okay, I've done all of my calculations, and I've got magnitudes for the force between all of these pairs. Okay, so first we're going to look at the chart at the forces on charge Q1. The first one in the box is the force of Q1 by Q2. Q1 and Q2 are both positive charges. Therefore, they're going to repel or push against each other. So the force that Q2 is putting on Q1 is going to be in the opposite direction. So it's going to be that way, which means it's in the x direction, it has no y component, and it's going to the left or to the negative. So we know that the force exerted on charge Q1 by charge Q2 is in the negative x direction, and we know that y is equal to 0. So we can go back and look at our numbers, and we see that it should be a negative 5.39 newtons. So I'm going to go ahead and fill that in. So we're going to look at the charge exerted on Q1 by charge Q3. But Q3 is a negative charge, Q1 is positive. They're opposite, opposites attract. So Q3 is going to attract charge Q1, and the charge is going to be attracted in this direction. Because it's a square, this angle here, although I didn't draw it like it, is 45 degrees. Looking in a little more detail, we can see that the x component is going to be positive. It's going to be going in that direction. And the y component is going to be negative, and it's going in that direction. And of course, this is a right angle, and because this is a 45-degree angle, pretty much all of these other angles are 45 degrees. Go ahead and do it like this, 45 degrees. We're going to find fx, and we're going to find fy. To find out those, we're going to take this vector here, the red one, which had a value of 3.6, and we're going to take 3.6 times the cosine of 45 degrees and 3.6 times the sine of 45 degrees. Of course, because it's a 45-degree angle, the cosine and the sine are the same value, so both those will give us the same number. The number, of course, is 2.55, and it's newtons. What we have to be careful of is the x direction is positive and the y direction is negative. So when we enter it in this chart down here, we want to have a positive x, 2.55, and a negative y, 2.55. The last force we have to figure out is between Q1 and Q4. Again, they both have the same sign. They're both positive charges. Like charges repel, that means they're going to be pushing against each other. So Q4 is going to be pushing against Q1, and it's going to go in that direction. That direction is the positive y direction. There are no x components. So the charge on Q1 by Q4 is going to be positive y. It's going to have 0x. And I just have to look over to my math work to find 8.99 newtons. I'm going to do the same analysis on each one of these corner charges. So for charge Q2, Q1 and Q2 are both positive charges. That means likes repel. So Q1 pushes on Q2 in that direction. Q2 and Q3 are opposite charges, Q2 being positive, Q3 being negative. That means they're going to attract, so Q3 is going to pull on Q2 in this direction. Q4 and Q2 are both positive charges. That means they'll repel, so the force on Q2 exerted by charge Q4 is going to be off in this direction. Looking at the charges on Q3, we have the charge between Q3 and Q2, attractive. So Q2 is going to pull on charge Q3 in that direction. Charge between Q4 and Q3, they're opposite charges, so again it's an attraction. So Q4 is going to pull on Q3 in that direction. And then of course the charge between Q1 and Q3 They're opposite, so they're attractive. So Q1 pulls on Q3 in that direction. Because I have cleverly picked a square, all of these angles here are 45 degrees. So for each one of these side forces, we're going to take the magnitude of the force, which would be some F. We're going to take F times the sine of 45 degrees to get the y component, and F times the cosine of 45 degrees to get the x component. But of course, the sine and cosine of 45 degrees is the same. With this information, now I'm going to fill out my chart. Okay, we've got our chart here. We've got it filled out. We've got the magnitudes in the right location. Are they an x factor or a y factor, or was it some combination of x's and y's? We have the correct signs, and the way we got those correct signs, whether it's positive or negative, is by looking at the forces between the two charges. Going back to our diagram, looking at those forces and saying, is it being pulled in the negative direction or pushed in the positive direction, or what's happening here? After we have all the x components and all the y components together, we're just going to add up our x and y columns. Okay, now I'm ready for that final bit. So what I really wanted to know is, what was the force exerted on Q1 by the combination of the charges 2, 3, and 4. I've got the x component of that force and the y component of that force. So now I have to recreate it as a vector. So to do that, the force on 1 by 2, 3, and 4 is equal to the square root of negative 2.84 squared plus 6.44 squared. So for my net force on charge Q1 exerted by the other three charges, I get 7.04 newtons. Now I need to know what angle it operates at. Remember, the way we find angles for vectors is we use the inverse tangent. Using that inverse tangent, I get theta is equal to negative 66.2 degrees. What do I mean by negative 66.2 degrees? Well, I could go back to my diagram, or I can just look at my components. If I think of the quadrants, I have, for this particular vector, it has a negative x component and a positive y. That means it's in quadrant 2, so it's going to look something like that. So for quadrant 2, I have to add 180 degrees to get my final angle. And I get theta is equal to 113.8 degrees. Taking a look at the second one, we're looking at the force on charge 2 exerted by charges 1, 3, and 4. So we're looking at the net force. We're going to look at the x and y components of that, which is 10.16 and negative 6.02. Put them in Pythagorean theorem, and we get that the magnitude of that force vector is 11.81 newtons, and the angle, again using the inverse tan of our y component divided by our x component, our angle is negative 30.65. Because we have a negative y and a positive x, we know it's in quadrant 4, so we have to add 360 degrees, and we get that the angle is equal to 329.35 degrees. For the force exerted on charge 3 by the combined charges 1, 2, and 4, we look at the x and y components, 20.53 and 13.34. Use Pythagorean theorem to get the magnitude of that vector, 24.48 newtons, and use the inverse tan to get the angle, which is 33 degrees, and it's in quadrant 1, so we don't have to do anything with it. So we have completed the problem and the end of this video. Thank you for your time.